In this video, I'll introduce you to the concept and expression for creating a projection vector. The vector created by projecting one vector onto another. Let's examine the graph on screen to illustrate this concept. Notice that I've arranged vectors A and B such that they share a starting point. I then drew a segment from the terminal point of vector A down onto vector B, forming a 90-degree angle. This is similar to shining a light perpendicularly onto vector B and measuring the shadow cast by vector A. I've labeled this shadow as vector C. We call this shadow the projection of vector A onto vector B, and we can calculate its magnitude using the following equation. We call it the projection onto B by A. This is standard notation, and this uses the dot product between vectors A and B, and we take that dot product and we divide it by the magnitude of the vector we are projecting onto, which in this case is vector B. This will give us the length of our projection vector. This equation uses the standard notation for the projection of vector A onto vector B. Be careful not to mix up the vectors. Remember that the expressions in this equation are scalars. You won't retain information about vector C's direction. However, conceptually, you should know that if the result is positive, it has the same direction as your base vector B. If negative, it has the opposite direction. As a side note, take a look at the angle between our two vectors A and B. Observe that the angle theta between these two vectors is acute. An acute angle between two vectors results in a positive projection vector. However, if the angle were obtuse, the projection vector would fall behind the base vector, resulting in a negative vector, one with the opposite direction of the base vector. We'll see this in our first example. Also, don't forget your right triangle trigonometry, because the expression given is not the only way to find the length of your projection vector. We have just created in this procedure a right triangle. And if we're given the information or able to deduce information about the magnitude of angle theta, then we should be able to find the magnitude of our projection vector using, in this case, our projection vector being the adjacent leg to our hypotenuse in this right triangle. We could say that the magnitude of our projection vector is also equal to the hypotenuse, which in our case is the magnitude of vector A, times cosine theta. This is because the length of vector C is adjacent to the known angle. All right, now let's go ahead and tackle an example. What is the value of the projection of the vector 7i hat minus 5j hat onto the vector negative 2i hat plus 3j hat? Since we're projecting onto the vector negative 2i hat plus 3j hat, we will consider this to be our base vector, vector B. And we are projecting 7i hat minus 5j hat onto it, so that's going to be our vector A. That said, it's not necessary that we graphically put this out, at least to start, because we have an expression that uses dot products. And the fact that we're given our vectors in their component form lends itself to calculating the dot product and their magnitudes fairly easily. So let me go ahead and write out what this looks like. A dot B, or in this case, our two vectors dotted together, will look something like this. 7 times negative 2 plus 3 times negative 5. This is the dot product of our two vectors. And based off the expression that's given for finding the magnitude of our projection vector, all I need to do is divide this by the magnitude of our vector B. The magnitude of vector B when given in components is simply just that Pythagorean theorem. So I can take negative 2 squared plus 3 squared. Now 7 times negative 2 is 14, and 3 times negative 5 is 15. So if I add those two together, very simply, I can get negative 29. And then negative 2 squared is 4, and 3 squared is 9. So 4 plus 9 is 13. So what I'm dealing with here is the square root of 13. Now, this is an irrational number, so the best I can do is an approximation if I want to give you something with a decimal. But if I put this in the calculator, I should get something similar to, or approximately, 8.04, negative 8.04, that is. Don't forget about this negative sign here. This value represents the magnitude and a hint at the direction of the vector, suggesting that it's opposite to our base vector, negative 2i plus 3j hat. Now, of course, we have the graph right here, so let's take a look at what this might look like graphically. If I wanted to go ahead and plot, and I'll do it in orange here, 7i hat minus 5j hat, that looks like me just following along the x-axis until I get to 7, 1, 2, 3, 4, 5, 6, 7, and then down until I get to negative 5 on the y-axis. 1, 2, 3, 4, 5. All right? If I'm using the origin as my initial point, then I can use the coordinates of my vector as its terminal point. Just like this. This could be my vector A. This is vector A in orange. And then for my vector B, what I'm trying to project onto, let's do this in purple so as to differentiate from our other graphical projection that we have over here. Negative 2, 3. So negative 2 along the x-axis and then positive 3 along the y-axis. I have this vector that comes up into the second quadrant, which I'm going to call B. Now, you might be thinking at this point this is a little bit interesting because there's not actually a way for me to project from the terminal point of vector A onto vector B such that it creates a 90-degree angle with vector B. That's going to be the case when you have a negative projection. The projection would fall behind the vector. That said, the way that you should think about it, or at least the way that I think about it, is I try to imagine that there is this infinite line that vector B lies on. And it's to this line that you are going to be drawing a perpendicular segment. So let me go ahead and actually use gray here. And I'm going to kind of help you visualize a line that extends past the endpoints of vector B. And it's onto this line that I'm going to go ahead and project the terminal point of vector A onto to create my projection. And then here in brown, you can see that my projection is here. My projection is here, and it is negative because it is in the opposite direction of vector B. If I go ahead and go through with the trigonometry and geometry required of finding the length of this leg, you'll see that its magnitude is approximately negative 8.04. So hopefully those visuals help you to understand what's going on with the expression. But depending on what information is given, you have the expressions needed in order to find the magnitude of that projection vector. Good luck on your studies. I'll see you in the next one.